In chapters 1 and 2, we talked about a count that came about through observing a number of successes out of a particular number of trials. So for example, we had W, which was our binomial random variable representing that count. It could have values of 0, 1, all the way up to n. The key was we were always, every single time, we had a success or failure over a certain number of trials. Now, there are other kinds of situations where we can have a count that does not arise through a success or failure kind of situation. It doesn't arise out of a certain number of trials. So for example, we could look at the number of arrests for a city per year. We could look at the number of credit cards an individual owns, the number of people arriving at an airport at a given time, the number of cars stopped in an intersection, and the number of people standing in line at Starbucks. All those situations do not fit into that binomial response count situation that we have been seeing before. So because of that, we need to use a different kind of probability distribution to model these kinds of situations. The probability distribution that we're going to look at is called a Poisson distribution. Most of you have seen that distribution, but I wouldn't be surprised if there's a few who have not. So we're going to do a brief review into that particular distribution shortly. Now you might also think of particular situations where you could have an explanatory variable that affects what happens for that count response. For example, the number of credit cards that a person owns is probably dependent upon their income level. And so because of that, we would like to have some kind of regression model that can help us model this count that has a Poisson distribution. So that's something that we're going to be doing in this chapter. We might also want to explore particular situations where you have a particular variable that actually is not really an explanatory variable itself. So for example, let's say that we wanted to examine the number of arrests that occur in cities per year. And if you wanted to compare Omaha to, let's say, New York City, Omaha has a population of about 500,000, New York City about, I think it's about 7, 8, or 9 million. Well, New York City is going to have probably more arrests in the city per year, just simply because there's more people there. And so city population needs to be taken into account when you want to make these comparisons. But city population isn't an explanatory variable itself. So we're going to look at ways to account for that. So let's take a look at the basics behind a Poisson distribution. So a Poisson random variable is a discrete random variable like a binomial because it's a count. It can have values of 0, 1, 2, and so on. So the non-negative integers. The function, for the Poisson distribution that helps us to measure the probabilities associated with these counts is called a Poisson probability mass function, and this is what it looks like. So the probability that my random variable y is equal to a particular value of it, such as 0, 1, 2, and notice there is no upper bound there, is equal to the exponential function evaluated at negative mu times mu raised to the y power, all that over y factorial. Mu is a parameter of interest for us that controls the shape of the probability distribution, just like how pi controlled the shape of a binomial distribution. Mu has to be greater than 0 here. Now sometimes you'll see people use a shorthand notation with this when you want to say, hey, y has a Poisson distribution, and so you might see people say y tilde, meaning distributed as, Poisson, po for Poisson, and then you put in the parameter mu just to help you see the item that controls the shape of the probability distribution. So our random variable y, again, then is our count. It's a count of the number of occurrences for an event, such as the number of credit cards you have, the number of people arriving at an airport. Now there are some interesting properties with this Poisson distribution. I'm not going to expect you to prove these properties. Rather, since this is an applied statistics course, we're going to simply state them and then use them as needed. So one could show that the expected value of y, meaning what I would expect the count to be on average, to be equal to this parameter mu that's in that distribution. Often in statistics we use the Greek letter mu to represent a mean, and so that's why we end up doing that here. But interestingly, the variance of y also ends up being mu. One could actually derive that, and you would see that in a mathematical statistics course. So this is kind of convenient, that both the expected value of y and the variance of y is equal to this parameter in the probability distribution. While that is convenient, it also can be something that limits the usefulness of a Poisson distribution. What can happen in actual application is that this variance can actually be greater than the expected value of y. When that happens, we have what's called overdispersion. So because of that, since that does happen in application, we will look at how to handle that later in another chapter corresponding to my book. For now, we're going to assume that that is not an issue. Now, if y1 through yn were independent with a distribution of Poisson mu, so like maybe we take a sample of size n, we have one count, that's y1, we have another count, that's y2, and so on. If we think of these as random variables, if you were to sum up these random variables, we still have a Poisson distribution here. It's just simply n times mu. If for some reason the mean was different for each of those corresponding random variables, then we have a distribution that is the Poisson with the sum of the mu's. We could form a likelihood function with our sample of size n. Maybe we want to find the maximum likelihood estimate for mu, for example. Our likelihood function is just the product of, let's say, n different Poisson distributions, where I'm using the k subscript here to represent k equal 1, 2, all the way up to n. I guess similar to what I already had done up there. One could find the log likelihood function, find the derivative of that log likelihood function, set it equal to 0, solve for mu, and you get the maximum likelihood estimate for mu. What it ends up being is something very intuitive, is just the sample mean. Notice how I put a hat on top of mu to indicate that this is an estimated parameter. Since we're talking about maximum likelihood estimation, we can then go back to our properties of maximum likelihood estimators and look at, for example, the estimated variance of mu hat. So notice how I have a var hat here to say that this is estimated, and then the estimated variance of mu hat, go through the calculations, and you end up with mu hat divided by n. Okay, well, let's talk about a walled interval for mu then. Well, how would we do an interval in this particular case? Same process as before. We take the estimate, mu hat, plus or minus the value from my standard normal distribution, the 1 minus alpha divided by 2 quantile, take it times the square root of the estimated variance of mu hat, which is all that right there. That's my confidence interval. And as you might expect, it does have some problems, similar to what we've seen with walled confidence intervals before, in terms of the true confidence level. But also there's another problem here, is that there is no constraint at all for having this, the lower limit being above 0, or 0 or above, I should say. So that's a problem. We saw a similar problem with respect to when we did a confidence interval for pi back in chapter 1. So what can be done? Well, similar to what we've done in other situations. How about we first find a confidence interval for the log of mu first? So here's my confidence interval for the log of mu. So this part right in there represents the estimated variance of the log of mu hat. One could derive that. You're not responsible for it. One could derive it using a delta method approximation. Then, since I have a confidence interval for log of mu, but I want an interval for mu itself, what can I do? Well, apply the exponential function to the lower and upper bounds. And there you have your confidence interval. One could also do hypothesis tests concerning mu as well. So I could test, is mu equal to some particular constant value, maybe like the number 3, versus not equal. One could form the wall statistic, where you take your estimator minus your hypothesized value of that estimator, divided by the square root of the estimated variance for the estimator. I could also form a score test statistic, and it has a very simplified form. Notice where mu0 ends up falling in that statistic. Again, you're not responsible for the derivation of that. So how would you decide on rejection of the null hypothesis? Well, both of these quantities here have an approximate normal distribution with it, a standard normal, I should say. And so we could use then a standard normal distribution to help us find p-values, to help us find critical values. In this particular case, we would of course have two critical values, a negative version and a positive version. Why? Well, take a look at the test statistic. Notice, we'll look at the wald here. Notice if mu hat is much larger than mu0 relative to what's in the denominator, well, you would think that there's evidence against the null hypothesis. So because of that, you're going to have a positive critical value to worry about. Also, if mu hat was much less than mu0 relative to what's in the denominator, then you would expect, well, that null hypothesis is probably not correct. So therefore, I'm going to have a negative critical value to worry about, as long as, let's say, mu0 is not equal to 0. And so then I would have two critical values. It's a two-tailed test in this situation. Make sure you understand then how you would form a corresponding p-value. It uses principles that you learned about in your first stat course. If you're not sure, please ask during our course. One could then, since I have a score test statistic, one could form a score confidence interval as well. How is this found? Well, simply look at all the possible values in mu0 such that the test statistic is within their two critical values that are possible. One could actually formally derive that and get this as then the corresponding score interval. And I have a question here. Which do you think is probably better between the wald or the score? Well, the score is going to be better. Here in that particular statement, though, I'm comparing that to the wald, the original wald interval here. And as far as I know, there hasn't really been research done into how well this interval works. And I would expect this interval to work much better than the regular old wald interval. Does it work better than the score? Probably not, but I wouldn't be surprised if it actually works rather well. So then I have another question here. Well, how else would you find a confidence interval for mu? Well, we've talked about other techniques in the past to find confidence intervals for parameters, such as maybe we could do a likelihood ratio interval, or maybe we could do an exact interval. In fact, you can. Take a look at my book for more details. Okay, so let's take a look at an example that helps further explain this topic. This example deals with the 33rd and Holdred Street intersection in Lincoln, Nebraska. This is your standard north, south, east, west intersection, and here's a representation of it on a map. Now, something that's important to notice here is that we have a fire station here. And this fire station is about 150 feet from the intersection. And so here is then an actual picture taken from the north east corner, I believe, of this intersection. So you can see, let me actually make this a little bit bigger. Hold on a second. So what we see here then is you see the stoplights at the intersection. This way is going south, and we see one car that is stopped at the stoplight waiting for a green light before it can go. Now you can imagine some situations where maybe you have a car here, do a very crude drawing, you have maybe another car here, another crude drawing. Now I'm going to stop doing these crude drawings here. And you have a whole bunch of other cars backed up. Here's the fire station. We have a garage here, and there are fire trucks that are in that garage. And you can imagine a situation where there's an emergency. The fire trucks are wanting to get out of their fire station, but there are, let's say, cars that are backed up here. Weird looking cars that are backed up here that prevent the fire truck from getting into the street and going and dealing with the emergency that's of interest. And so because of that, you see a sign here. It says, do not block the driveway. However, many times, my office is right outside this intersection. Many times I've seen cars block that driveway. Part of the problem is that there actually is a tree. It's hard to see, but there's actually a tree that kind of hangs over here. I'll kind of draw a tree here. And oftentimes, if you're driving this direction, you do not see the sign until it's too late, and you might not be able to stop in time to avoid blocking that driveway. Okay, so that's some background on the situation. And because I'm a statistician, I'm very curious about, well, how often is this driveway blocked? And so what I decided to do was I actually took a sample of 40 consecutive stoplight cycles from 3:25 p.m. to 4:05 p.m. one day. It was a regular work day, you could say. And for each stoplight cycle, meaning red light, green light, red light, green light, every time it was a red light, I counted then the number of cars total that were backed up in that intersection. So for the first time that I did that, I saw 4 cars there. Next time I saw 6 cars, and so on. My entire sample is in a file called stoplight.csv. A key element to understand here is that for consecutive stoplight cycles, there was never a vehicle that, let's say, was stopped at a stoplight, then went green. There was never a time where that vehicle didn't make it all the way through the intersection before the red light came about, meaning a car never had to wait more than one stoplight cycle to get through the intersection. The reason why that's very important here is because then that would say that there's some kind of dependence from one cycle to the next. Here we can roughly treat then my sample then as a random sample. What happens on one cycle doesn't affect another cycle. Okay, so that's the setup here. Let's look at to see, can we use a Poisson distribution to help understand what is happening in this intersection? So to do this, I'm going to come back over here to 10. Let me actually go up to the top. And let's see here. I'm actually in the wrong file. There we go. So here's where my data is. And I'm going to simply calculate the sample mean and the sample variance. Now remember, the sample mean is the maximum likely estimate for mu. So I have 3.875 from my data. But if I were to calculate then the sample variance as well, I get 4.3. Let me come back over here. Because the expected value of y is equal to mu, the variance of y is equal to mu. If I were to look at the sample mean and the sample variance, I would hope that they would both be approximately the same. If they were, then this is one element here that suggests, hey, a Poisson distribution is probably appropriate for this data. Take a look what we get. They're not too far apart. So based upon that, that's one bit of evidence to tell me, hey, a Poisson distribution is probably okay with this to work with for this data. But we can go further. Suppose I use the table function. Let me go ahead and come back over here. We've seen the table function before. Suppose I use the table function to help summarize the frequencies that I have 1 car, 2 cars, 3 cars stopped in my intersection. So for example, 5 times in my sample, 1 car was stopped in my intersection. And then what I'm going to do is calculate the relative frequency for each of those particular occurrences. Meaning, I take what's in my results from table and I divide by my sample size. That's my relative frequency. let's go ahead and take a look at it then. So 0.025 at the time, there was no cars. That was 1 divided by 40. 5 divided by 40 is 0.125, and so on. Now, for some comparisons I'm going to make a little bit later, I'm going to add some zeros at the end of my vector of results. Because it says that at 9, my, let's say, relative frequency, my proportion of what occurred, at 9 the proportion was 0. At 10 the proportion was 0, and so on. Next, what I want to do is compare those relative frequencies, those observed proportions for each of those counts. I want to compare them to what a Poisson distribution would tell me about it. And so, like what we've seen with the binomial distribution, there is a function called dPois, set of dbinom, that helps me find probabilities associated with a Poisson distribution. So the way this works, let's say if I want to find, let's say, the probability that y is equal to 3 when mu is equal to, let's say, 10. How would I do that? I use dPois x equal 3. It uses x rather than our y. And then instead of saying mu, it uses lambda as its syntax. And so if I type that in and run the code, this gives me my probability that y is equal to 3 if mu is equal to 10. Okay, so that's how that function works. What I want to do, though, for our situation here is I want to find probabilities associated with having a count of 0 cars, 1 car, all the way up to 15 cars. So I let y get the results from 0 to 15. So 0, 1, 2, up to 15. Next, I'm going to use the dPois function where x is going to be equal to y. So I'm going to have 16 probabilities come back to me. But what do I use for my lambda? Well, how about we use the maximum likelihood estimate in this particular case? So I say mean of the vehicles. I round the results, put them into an object called prob. And then how about we display this nicely in a data frame? And this is what I get. So when there's 0 cars, Poisson distribution tells me that probability should be 0.0208. I observed 0.025. Very close. 1 car, Poisson probability distribution tells me 0.08. The observed data is 0.125. It's a little bit off, but not too much. And so what I could do then, let me come back over here to Word, is how about we graph these? And that's what I have here in the notes. I have probability on the y-axis, so this will be probability from Poisson distribution, or essentially the relative frequency, the observed proportion of times I got a particular count. On the x-axis, I have the count, the number of vehicles. So for example, what we just saw before, here is 0.0208, here is 0.025, corresponding to what was observed versus the Poisson. What we're looking for here is a similar shape. Roughly speaking, we do have a similar shape. We have, at 3, this is probably the biggest deviation. But otherwise, everything looks pretty similar. Again, we only have a sample size of 40 to begin with, so we can't expect perfection of a matching here. But what this is telling me is that, I'm pretty satisfied that a Poisson distribution is a nice approximation to what's occurring in reality. Now, how did I do this plot? I want you to see this on your own. Basically, what I did was, without going into all the details, I graphed my y's on that possible values of y on my x-axis, where I just moved it over a little bit, 0.1. And that's what gives me my black lines here. Okay? The reason why I did that is because I wanted to do a direct comparison to what was observed. To get then the red lines, I use a function called lines, where notice I put my y's in there, but I just move them over a little bit to the right. We've seen this before with plotting the binomial distribution. I do type equal h, means how high are you going to plot the stuff. That corresponds to what I have for the y argument. Also, one thing that we haven't really used, AXT stands for x-axis tick marks. N means do not put them there. And rather, I'm going to control exactly what those x-axis tick marks are by using the access function. Side equal 1 corresponds to my x-axis. Where do I want the tick marks? 0 to 15. And so that's how I got that plot. Okay, so let's talk about now how we can do a walled confidence interval. So I take my mu hat that I've found right here, just from using the sample mean. I find my quantile for my standard normal distribution. I take it times the square root of the estimated variance of mu hat. I get an interval of 3.26 is less than mu is less than 4.49. So that's my 95% confidence interval. So I didn't mention alpha was 0.05. That's my 95% confidence interval for mu. What if, though, we use the walled confidence interval using first that log transformation? Well, I just simply program in my corresponding formula that we saw before, and there's my interval, 3.31 to 4.54. So we see a little bit of difference from the other walled interval. Here is my corresponding score interval, 3.31 to 4.53. Notice how close that is to this walled interval that starts with the log transformation. That's kind of interesting. Now, you might also be wondering, well, what if you were just to use regular old t distribution-based confidence interval for mu that you learn about in your first stat course? So in other words, take y bar plus or minus a 1 minus alpha divided by 2 quantile from the t distribution with n minus 1 degrees of freedom times s, which will be the sample standard deviation, divided by the square root of n. That expression should be familiar to all of you. If you were to do that interval, this is what we get, 3.21 to 4.54. And you can compare how that upper interval looks very similar to what we had. The lower interval is a little bit different. Now, let's take a closer look at this relative to the actual application that we're interested in. Suppose all vehicles are 14 feet long and the distance between cars is 4 feet. So in other words, you have 18 feet corresponding to each vehicle at an intersection. Is every vehicle, every car, every truck 14 feet long? No, I'm just saying, let's suppose that is. This suggests that 9 vehicles or more are needed to block the intersection. To block the driveway for the fire station. So if I take 150 divided by 18, I get 8.3. So 9 or more would actually block that driveway, preventing the fire trucks from entering the intersection. Given what we just did here with that Poisson distribution, what would be the estimated probability that that would happen? And so what I can do is find probabilities with the Poisson distribution, also using the p-poise function. What p-poise is going to do is find the probability that y is less or equal to little y. In other words, this ends up being actually the cumulative distribution function. And so if, let's say, p-poise was, if I use p-poise, let me actually come over here to our, excuse me. Let's say that I'm interested in, let's say, the probability that y is less or equal to 8, or we'll do 9. And let's say that my mu was 10. Okay? This expression that I just typed is going to find the probability y is less or equal to 9 if mu is equal to 10. And I get 0.457. Now, if I wanted, let's say, the probability y was greater than 9, so let me go ahead and make a little change here. I can use the complement, and I get that. So I take 1 minus that corresponding probability using the complement. Now, in this particular case, again, I want to know what's the probability that y is going to be greater than equal to 9 for us. So in that particular situation, then, I could use 1 minus the probability y is less or equal to 8. Remember, we have a discrete random variable, so that's why it's important to be careful about these, the equal signs there. This would be equivalent to the 1 minus the probability y is less than 9. And then I say 1 minus p poise q equal 8. Q stands for quantile. This is just this part right there. And then I say lambda equal, and well, what do I use for mu though? Well, how about we use as estimated value, mu dot hat. And so the probability then that the intersection will be, the probability the driveway will be blocked is rather low, 0.018 about. But remember, this is just for the intersection during one stoplight cycle. Typically, as we saw, there's essentially one stoplight cycle per minute. So what if we look at over 1 hour? What's the probability that that intersection will be, that driveway will be blocked at least once? This is where we can then now use the binomial distribution. So essentially we have 60 trials. We have an estimated probability of success, or probability of being blocked, of 0.017. So how about we just use that for pi so we can get an estimated probability that the intersection, not the intersection, the driveway will be blocked at least once. So I want the probability W is greater than or equal to 1. That's equal to 1 minus the probability W is equal to 0. And if we do the calculation using d binom, as what we've seen before, I get 0.66. So this is really a significant probability then that this intersection will be blocked. If somebody doesn't, let's say, see that sign about, don't block that intersection, which does occur. It's hard to see that sign. So why do you think then, we have some questions here. Why do you think, what do you think will happen to this probability that we see here during rush hour? Well, during rush hour, there's going to be more vehicles out there. Remember, I did mine in mid-afternoon, my sample from mid-afternoon. So if there's more vehicles out there, I would expect that probability to be higher. How could we take into account then the different time periods of day? At, let's say, midnight, there's probably going to be a lot less cars out than there is going to be at 5 p.m. than there's going to be at 3 p.m. So how can we take into account that time? Well, what that is saying is that mu, my mean count, is essentially dependent upon time. So how about we have a regression model where we have time be an explanatory variable to estimate mu? We could use let's call it a Poisson regression model to further analyze this kind of data. Now, again, this is an estimated probability here. So you might be wondering, well, okay, it's an estimate. How about we find a confidence interval for it? And one can do that. And in my additional program associated with this example, the name is at the very beginning of the example, I show how one to do it. You're not responsible for it. It actually requires a delta method approximation to do all this. There are some semesters where I would have students expected to understand how to do that, but only if I say something that you are responsible for it do you need to worry about it. But one could find an interval, and the interval is 0.33 to 0.99, so it is rather wide. There's a lot of uncertainty with it. How can we take care of that uncertainty? Take a larger sample size. Sorry, I only had 40 minutes on one day to take that sample, and so that's why I have a low sample size. Okay, so this section introduces you to a new way to deal with counts, where counts here in this particular situation don't necessarily have an upper bound. It's not meant for, let's say, a number of trials that are repeated in terms of where you have a success or failure on every trial. And so we use a Poisson distribution to model these kinds of situations. This section then gives you an introduction to inferences, then corresponding to the Poisson distribution and its particular parameter mu.